6.5 is the central limit theorem. This is going to be very similar to what we did back in 6.2 and 6.3. Really, the only change is going to be, instead of finding something for one single item, we're looking at a sample of items. So going through this, we have our distribution. When we go through these distributions, we are going to be changing our mean and our sigma, our standard deviation, depending on the size of our sample. So going through this, n is going to be your sample size, and then mu is always your mean, and then your sigma is always your standard deviation. Now you're going to see this new notation here of this mu with an x bar, sigma with an x bar. That represents your new mu, your new sigma, given we have a sample size of bigger than 1. So things change a little bit if we have sample size bigger than 1 as we go through these. So for example 9, it says, suppose a team of biologists have been studying a certain children's fishing pond. Let x represent the length of a single trout taken at random from the pond. This group of biologists has determined that x has a normal distribution with mean of 10.2 inches and standard deviation of 1.4 inches. What is the probability that a single trout taken at random from a pond is between 8 and 12 inches long? The important part here is single trout. So that means we do not have to change our numbers because you're just looking at one single trout. If they would have said, what's the probability of 10 trout taken at random, then we have to do some changing to our numbers. So for example, 9a here, it's going to be exactly like we were doing in 6.3. There is no change at all yet. So remember what we did. If they want the probability that we are between 8 and 12, they are saying, what's the probability that x is between 8 and 12? So going through our steps, we have to first change x to z, then we can use our probability table. So remember, z is x minus mu over sigma. So we'll start off with 8. 8 minus 10.2 over 1.4. So we're going to subtract the top and divide. Remember, 2 decimal places. So I have a negative 1.57. Then our other z. X minus mu over sigma. So I'm doing 12 minus 10.2 over 1.4. Again, subtract, hit enter, then divide. And we get a 1.29. So now you need to look at your tables. You should be really good at looking at your z table now. So look at your z table for negative 1.57. So look at the negative 1.5, and then you want to go over to the 0.07. So you should have found then 0.0582. Next, look at your table. You want 1.29. So go to the 1.2, and then you want to go to the 0.09 column. So when I have 1.29, that area should be 0.9015. Now remember, we have 2 numbers. When we have 2 numbers, after finding your areas, we have to subtract the 2. So 0.9015 minus 0.0582. So we subtract our 2 numbers to get our probability is 0.8433. Now, part B is going to change it up a little bit. So for part B, we're going to have to use the new sigma and the new mean going through these. So it's still the same problem, but now they're saying we've got 5 trout. So it's not 1, it's 5. So that means we have an N as we go through this. So that means then that our N is equal to 5. Because we have 5 in our sample. So now we have a new mean, and it's written as the X bar. Now, if you go to the last page, it says the new mean is equal to the old mean. So the mean never changes. We just write it differently. It's still going to be 10.2. However, sigma does change. To find your new sigma, you take the old sigma divided by the square root of n. So in our problem then, we're going to take 1.4 divided by the square root of 5. Now when we divide these, we get about 0.63. Now you can do however many decimals you want. The more decimals, the better the estimation. Because if you make less decimals, your number is not going to be as close as what it should be. So more is better when you go through it. So now when we want the probability between 8 and 12, we have to use these two numbers to change to our z's. So we're not using the 10.2 and the 1.4. Now it's 10.2 and 0.63. So when we go through for our z formula, it says take x bar minus mu x bar over sigma x bar. So we're still looking at our probability between 8 and 12, but now it's x bar because we're taking the average of those 5 data. So I'm still going to go through this just like I did my last problem, except now x bar is 8 instead of x. I've got 10.2 for my mu. Now sigma has changed, so 0.63. When we do that, we get negative 3.49. We're going to do the same thing then for our 12. So if I have minus my mu sigma, so 12 minus 10.2 over 0.63. So that should give me a 2.86. So those are going to be my two new z values. So now I've got when z is negative 3.49, I want to find my area. And I want to find when my z is 2.86, I want to find that area. So again, you are going to your table just like we've done before. Look for negative 3.4 for your z, and then go all the way over to the 0.09 column. When you do that, you'll see 0.0002. Now we need 2.86. So go to 2.8 for the z and go over to the 0.06 column. So 0.9979. So I have 0.9979. So we want to subtract those two numbers then. When I subtract them, I get 0.9977. So if you notice between your two probabilities, this one's higher than the other probability. Even though we're using the same numbers, having more in our mean will eventually change the probabilities that we had. So just as a heads up, when you go through these, you're not going to get the exact same answer for both. When you have one versus changing your sample, the numbers will change. They might go up, they might go down, but they're not going to be the exact same for your probabilities. And just as a side note, I am recording this at school, so when the announcements come on, that is what you're hearing in the background, because I'm recording this at my school. Okay, standard error. You might see the term standard error sometimes in WebAssign or in the directions or anything like that. Standard error is just the new sigma. So that's going to be your old sigma divided by your square root of n. Now, our central limit theorem. We can use this anytime that we have a sample size of 30 or bigger. It's going to follow that we can change our mu, our sigma, and find the new z, as long as n is bigger than 30. Does not matter what kind of distribution we have. Now, if n is smaller than 30, we have to know first that we have then a normal probability distribution. It must say normal if your n is smaller than 30. And this is going to be the same thing for later on other sections. So whenever we're talking about distributions, if it's smaller than 30, then you have to have the word normal there or something that explains that we have a normal distribution. But if your sample is bigger than 30, it does not matter what the distribution is. It can be any type of distribution, but it will follow a normal type of distribution then if it's greater than 30. So we could still use our changing as long as the n is bigger than 30 if we don't know it's a normal distribution. Okay. So for our last two, we're doing the exact same thing that we've been doing. So I have a certain strain of bacteria occurs in all raw milk. Let X be the bacteria count per milliliter of milk. The health department has found that if the milk is not contaminated, then X has a distribution that is more or less mound-shaped and symmetrical. The mean of the X distribution is mean of 2,500. Standard deviation is 300. In a large commercial dairy, the health inspector takes 42 random samples of milk produced each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain the sample mean bacteria X bar. For part A, assuming milk is not contaminated, what is the distribution of X bar? We have an N that is bigger than 30 because they tell you 42 samples. So that means that X bar is normal. Again, since n is greater than or equal to 30, we have a normal distribution. Now, because we have X bar, that means we're going to have a mu X, which remember, mu X is the same thing as the regular. And we're going to have our sigma X. So for sigma X, we have to take then old sigma over square root of n. So we are going to take then 300 over square root of 42. So when I do that, I get about 46.3. So assuming the milk is not contaminated, what's the probability the average bacteria count, X bar, for one day is between 2350 and 2650 bacteria per milliliter? So going through this, the 2350 and the 2650 are your two X's. So we're finding the probability 2350, if I can write, 2350 less than X bar less than 2650. So you're going to change to your Z. So we subtract those two together. And then we're going to divide by 46.3. So I've got a negative 3.24. So same thing down here, subtract and divide. have a positive 3.24. Now you're finding the areas that go with both of these. So again, you're going to your table, looking for negative 3.24. Then you're looking for 3.24. So for negative 3.24, negative 3.2 for your z, 0.04 then for your column, and we've got 0.0006. For 3.24, look for 3.2 on your z, 0.04 for your column, and we get 0.9994. Now we subtract. So when I subtract these two, I get 0.9988. So they are saying then that we have a 99.88% chance of all the bacteria count being between 2350 and our 2650. So at the end of each day, the inspector must decide to accept or reject the accumulated milk that has been held in cold storage awaiting shipment. Suppose the 42 samples taken by the inspector have a mean bacteria count that is not between 2350 and 2650. If you were the inspector, what would be your comment on this situation? So think about this. If there's a 99.88% chance of being in between 2350 and 2650, that means there's a 0.12% chance of being outside of that range. So if you're outside of that range, that's a not very high probability of that occurring. So that means then something's wrong with the milk because you are only at a 0.12% chance of being outside of this range. So again, there is something wrong with the milk. Since the probability for this happening is 0.12%. Okay, so I want you to try this one. It's just like our last one, so pause the video, come back to me, and see if we get the same answers. So we have, in mountain country, major highways sometimes use tunnels instead of long winding roads over high passes. However, too many vehicles in a tunnel at the same time can cause a hazardous situation. Traffic engineers are studying a long tunnel in Colorado. If X represents the time for a vehicle to go through the tunnel, it is known that the X distribution has a mean of 12.1 minutes and standard deviation of 3.8 minutes under ordinary traffic conditions. From a histogram of X values, it was found that X distribution is mound-shaped with some symmetry about the mean. Engineers have calculated that on average, vehicles should spend 11 to 13 minutes in the tunnel. If the time is less than 11, traffic is moving too fast for safe travel in the tunnel. If it's more than 13, there is a problem of bad air quality, so too much carbon monoxide and other pollutants. Under ordinary conditions, there are about 50 vehicles in the tunnel at one time. What is the probability that the mean time for 50 vehicles in the tunnel will be from 11 to 13 minutes? So first off, it says, let X bar represent the sample mean based on samples of size 50. Describe the X bar distribution. So since we have 50 vehicles, our N is bigger than 30. So that means X bar is normal. So now we've got to change our mu, which is just the same, so 12.1. But we do have to change our sigma. So we are taking 3.8 and dividing it by the square root of 50. So now we're going to use that information to go through and find our probability between 11 and 13. So you've got to change to your z. So you should have gotten z's of negative 2.04 and 1.67. Now you went to your table. When I have 1.67, we should have gotten a 0.9525. And when I have negative 2.04, sorry, sometimes it does stop on me. There you go. And then we've got negative 2.04. My area should be 0.0207. So we got to subtract. So when I subtract those two, I get 0.9318. There you go. So that's my probability then for 11 to 13 minutes. So they want you to interpret your answer to part B. So they are saying 93.18% of the time they are between 11 and 13 minutes. So that means 93.18% of the time there are no safety hazards and they're moving at the correct speeds they should go. So again, as you go through these, every time, first change your sigma only if your sample size changes. If it says single, you don't change anything. If it says you have a sample size, that's when you have to change your sigma. So then find your z's, find your areas, and then subtract if you have two numbers, or use your table if it's less than or greater than, just like we talked about back in 6.3.